So we were discussing the idea of the Bayesian approach and how we can view the Bayesian statistic from the lens, like through the lens of decision theory. So the idea was that in the frequentist approach or the decision theoretic approach, we started with this probability model for our data, which is a parametric family of probability distributions. And for frequentist, this parameter is fixed. So it's, let's say, deterministic. It's unknown, but deterministic. In the Bayesian framework, we're going to assume that this parameter itself is random. There is a distribution on it. And the way we're going to interpret this T theta is as the conditional distribution of x given theta. Okay, so if you want to be explicit, the probability of an event under theta is basically the conditional distribution of x given theta. That's the kind of interpretation we assign to these probability distributions. And because we also have a distribution on theta, we get a joint distribution on theta and x. So we have a full specification of the distribution of this pair. Okay, and then the frequentist, so I'm using lambda here. It's not a good notation. I think probably Keener uses it as well. I forgot who uses this, but it's, yeah, unfortunate notation, but it's like a distribution for theta. That's the prior. We'll see, like I use different notations later. So the frequentist risk was the expectation of this loss under T theta, and now we're interpreting this as the expectation of this quantity conditional on theta being equal to theta. And if you like plug in the random theta here, you can think of like replacing this theta with just a random theta, you would get this risk when evaluated theta is just a conditional expectation of the loss conditional on theta. So they're both, and there are two sources of randomness, theta and x here. And so the base risk would be if I take an expectation of this. Okay. So this is only random because of theta. So here I'm averaging out over the distribution of x conditional on theta. So there is some sort of a smoothing going on. For every theta, I'm going to average out this over the possible values of x, basically. Now this is random in theta, and I take an expectation. Okay, and if you write down this expectation, it's just like this. So it's you can see that's a weighted average of the values of the risk, where we weight thetas by their prior sort of weight. If you're not comfortable with this, just imagine like, you know, we're going to do like discrete cases where the parameter space is discrete. Suppose omega is theta up to theta k, and then the prior would be just like a vector, lambda 1 up to lambda k. These are the probabilities. So lambda I would be the probability that theta is equal to theta I. Okay, and this just would be a summation r theta I delta and lambda I. Okay, so that's like a weighted average. So we weight the values of the risk, and so that would be our base risk. And then we can talk about what decision rule minimizes this, assuming that we fix the prior. If you are like careful, you would see that we actually, like if you're a frequentist, if you have a frequentist mind, you'll see that we actually didn't solve any problem. We just exasperated the problem, because now this is a function of the prior, and I can think of like overall priors, but that's not what Bayesians do. Okay, so like we traded off like the parameter for now, like the set of all priors. Now I have to worry which prior I choose. But if you're a Bayesian, the prior is fixed. You know the prior, there's just one prior. So once you fix the prior, this is really a function of delta only. And now we have a number, we can ask what is the minimum. value this and what decision rule achieves that. So this is the base risk. I mean, this is like different ways of writing it. You can figure that out for yourself. The base rule is the one that minimizes the space risk. Okay, so that's what we had there. Or if you want, just summation. So the base rule is the rule that minimizes this over all possible decisions. And you're going to write it like delta lambda because it depends on the prior and also depends on the loss. Okay, questions? So this was last time, and we're now just going to minimize this. The minimum is really easy, like the minimizer is sort of easy to find. There are different ways of doing it. Maybe like intuitively, what happens is this is the intuitive approach. So you have r theta delta x sorry, so this is the intuitive way. So this is the base rule is the expectation of L theta and delta x, or both theta and x. That's another way of writing it. So I can write it as expectation of L theta delta x conditional on x first, and then I'm gonna take an average. So this is by smoothing property, right? And this would be like integral. If you write on the outer one, it's like L theta delta x conditional on x being equal to x, and then I'm going to write p theta or p of x, let's say. Dx, this is the marginal distribution of x. Okay. And you can write it in measure theory form, but it's fine. That's the outer expectation, right? But because I'm conditioning on this, I can just replace this with little x. Now this is a deterministic number. And if you think a little bit about this, you'd see that if I minimize this for every x, just for every x, the decision delta x is different. So if I minimize this for every x, then I'm going to minimize the overall thing. So just my problem reduces to figuring out for every x, what minimizes this conditional expectation. And we're going to say that the Bayes rule is really exactly what minimizes this. So this is the Bayes rule is going to be arg min over L theta and D. I'm going to put it like a generic thing here. Conditional on x, and then minimize over D. So for every x, whatever, so decision here is like a number. So this is up to me to choose. I'm going to put a D there and then minimize over D, or A action. So this is the dummy variable. So whatever A that minimizes it for a particular x, that would be my decision for x. If you give it a moment of thought, that's going to be the optimal rule. Okay. Because for every x, I just have to choose this separately. They don't have anything to do with each other. And because of this, I'm going to average over. So at every point, if this is minimum, then it has to be minimum overall. Once we argue this is good enough, but you can formally prove it. So that's the formal statement. It says that just the same thing here down there. So there is a minor condition that there exists a decision rule for which this Bayes risk is finite. This is a technical condition. Otherwise, if there is no one, then everything has infinite Bayes risk, and then you don't have to worry about the optimal. So the minimizer. Okay, so the second condition is that this is called the posterior risk for obvious reasons, because it's the risk because of the expectation of the loss, but under the conditional distribution of theta given x, you remember that this is called distribution of theta given x is the posterior. It's called the posterior. So you're taking the expectation under the posterior of this loss, so it's reasonable to call this the posterior risk. So the posterior risk has a minimizer for almost all x, and then I mean you're not going to worry about the measurability issues and stuff. So this guy, then the result is that this is going to be the Bayes rule, and the way to prove it is that by definition, for every other decision rule, this is going to hold, because for that particular x, delta, this is the minimizer of the second argument, or the second argument. So you can argue very easily for yourself that because of the way that we chose this, conditional on x, this is fixed, a number, this is another number, and this is like some a, this is a star. So this is the best choice for that x. So that minimizes the fact that it's a minimizer of the posterior risk makes this inequality hold for almost all x, and then you take the expectation of both sides, use monotonicity and smoothing property. So that's the formal way of arguing. If I take the expectation of both sides, this gives me L of theta delta bigger than or equal to expectation of L of theta and delta lambda. So this side is the risk of Bayes risk of delta. This side is the Bayes risk of this other estimator, and it shows that this holds for any delta. So this has to be the minimizer. Yes.
So for each small x, you have a minimizer a, and if
Yes.
you have a different small x, will a the different.
Yeah, so that's why I wrote the minimizer as delta star of x. Yes.
But it's more like function of the x.
It is a function of x, so that's why it's written like this, right? So that's why it's a rule, right? So for every x, you get a value like the minimizer over this would be a number, but that number changes as a function of x. So it's really a function of x. So that's why it's a decision rule. Yeah. Good point. Any other questions? So this is a simple result, but it's like a very interesting result nonetheless. And just a very there's a very straightforward optimal rule if you're looking at the problem from a Bayesian perspective. Okay. So in order to find the optimal rule, you have to be able to calculate this posterior risk, and oftentimes you'd use the Bayes rule to figure out the posterior distribution. So I'm using the notation here, which is a little bit cumbersome, but the idea is like the posterior, if everything has a density, posterior of x theta given x is, this is the usual like elementary probability Bayes rule. P of x given theta times P of theta divided by P of x. That's the Bayes rule in terms of densities. I'm using different notations here. So pi for the prior here, that's the density, prior density. This is the posterior density. This is what we call the likelihood. And this M of x is really that P of x, using different notation so that not all of them are P, but this is called the marginal distribution. So x has a marginal distribution. Once you marginalize out theta, there's a joint distribution of x and theta. Once you marginalize out theta, there is this M of x, which has its own uses. For example, this should be, for example, M of x here. That's the marginal density. But if you want to calculate the posterior, it doesn't matter because the posterior, let's say density, posterior density is a function of theta. And this just acts as the normalizing constant. So if you, it's hard to calculate, you might say that the posterior is proportional to this. This is often what people do in calculations. And then maybe they recognize the form of this. And then someone else has done the integration. So there we'll see examples. So you don't have to calculate the marginal distribution. This gives you the shape up to a constant. This is a constant as a function of theta. And so sometimes it's convenient to write that like this. The posterior is proportional to the likelihood times the prior. And you see why I call this the likelihood, because at like in this formula, we're looking at the conditional density as a function of theta. That's what we call likelihood, right? So posterior is the product, like proportional to the product of the likelihood times the prior. So that's like the dogma in Bayesian statistics, posterior proportional to likelihood times the prior. That's Bayes' rule, or like this just summarizes the entire Bayesian approach. And we'll see examples of this, okay? So let's see what happens. So any questions? So let's see what happens if you have the L2 loss. I'm just going to assume that this is theta. So you have theta minus a squared. Then the minimizer of the posterior risk. There are different ways of showing it, but so what we want is to minimize expectation of the loss, which is theta minus a squared conditional on x. If you minimize over a, the argument, it's not hard to see that it's just the conditional expectation of theta given x. Okay, there are different ways of doing it. But the easiest is to expand. It's a quadratic. As a function of a, it's a quadratic. And you differentiate it equal to 0. And you get the result. An easier thing to do later, if you want to do like other calculations, you can also ignore this part for simplicity, because the posterior is just the distribution. So you can think of just putting a distribution on theta, whatever it is. If I figure this out, what is the minimizer? You can even do it on the prior. So the minimizer of this is the expectation. You probably know this because this is the best approximation of A in terms of theta, right? If you remember, you're projecting basically theta and the space of constant function. So that's given conditional expectation of theta given constants, which is this. So once you figure out the solution, then you add conditioning. So it's helpful. It's just gonna this is gonna be a property of the distribution of theta, whatever distribution it is. Here is gonna be that same property on the posterior distribution. So minimizer of the quadratic risk, or like risk for the quadratic loss would be the Bayesian like quadratic loss would be the mean of the distribution. So if you do it for the posterior, it would be the posterior mean. If you change it, for example, to the L1 norm, then the minimizer, the solution would be a median. Solution wouldn't be unique, but it would be the median of the distribution, and so it would be median posterior median. In some other cases, it would be the mode of the distribution that you might see in your forward problems. But it would be a feature of the posterior. For quadratic loss, it would be the posterior mean. So if you really care about the optimal Bayesian decision rule for quadratic loss, it would be just posterior mean. So you calculate the posterior, compute the mean, that would be your best estimator, that a minimizer of Bayes risk. Sounds good. Although very simple, but it's like far-reaching sort of result. You can do classification, for example. The thing about the mode that I mentioned would appear in the context of 0-1 loss for classification. You can do like cost-sensitive classification. The cost of different classes could be different. You can figure out all those using what is the optimal one in each case by just solving this problem, just solving this optimization problem, which is often not hard. The difficulty is like in general that the posterior distribution is not easy to figure out. So even in the parametric cases, maybe there's no closed form, so you have to sample from it. Usually in the Bayesian approach, we come up with a complicated model. It's like you can write something like this, but there's no easy way to sample from this. There's no easy way to normalize it. And so people resort to what? to actually do the Bayesian analysis. Anyone knows how to like deal with the fact that usually the posterior is complicated? So they resort to like numerical approaches, right? So MCMC, Markov chain Monte Carlo, a very special case like Gibbs sampling. They try to like come up with a Markov chain that gradually produces samples from the posterior. And once you have the samples, for example, you can approximate this by the empirical mean. Like if I have a sample of size n from the posterior, I'm just gonna do like j from 1 to n, or t from 1 to n, theta t. That would be my estimate, assuming that these are generated from the posterior. So I produce a sample of size n from the posterior and then take the average, empirical average, right? So you can't write down the posterior, but you probably can sample from it. Yes.
Sorry, I think you might have said it while you were going to the difference between the conditional and the regular distribution. Why is the R domain the mean of theta given A? I'd rather not just E of theta. Or sorry, given X. So it's E of theta given X, but it seems like you should like the thing which minimizes the expression that looks like that is just the mean, not the mean given X equals X.
It's the mean of the distribution of theta. And because we are taking the distribution of theta, when you compute this expectation, you're taking the expectation with respect to the conditional distribution theta given X. So the solution of this would be the mean of that distribution, which is like the conditional distribution of theta. So everything is we're working on the assumption that we condition on X. So it changes all the probability distribution, all the expectations, everything is now with respect to that condition. That's why I said you can just ignore that, just figure out what happens for a general like distribution of theta, and this is the general distribution happens to be the conditional distribution. Yeah, just once you understand it, it's just you can carry it around or just drop it for your like to simplify the notation and then put it back together at the end. Okay, so we now know what the decision-Bayesian optimal rule is. I'm not going to talk about MCMC approaches. You're going to probably see it in great detail on the courses. Okay, so there's a whole like avenue here. So how to do these Markov chain Monte Carlo approaches to produce samples. They're interesting. They're like fascinating. That they're actually the things that made Bayesian statistics popular. Say in the 90s, like there was like an exponential growth because people figured this out and computers were like available. Then you could just produce these estimates, and they it made it much more attractive, the Bayesian approach. Okay, questions? So let's see a couple of examples. This was our original model. So we had the case where we were dealing with a sequence of coin tosses, and we wanted to estimate the probability of the coin coming up ahead. There we had like x1 up to xn, Bernoulli theta. But if you think a little bit about this problem, given what you know now, there's a sufficient statistic here for theta, which is the sum of x1 up to xn. So statistically, this model can be reduced to just summation of xi. So I can just form this, and this has the binomial and theta. So statistically, the two models are equivalent in a sense. Okay, statistical information. So now I'm going to call this x here, and just don't worry about the sequence. There's no point in keeping the sequence. Now my model is just Bernoulli, binomial n and theta. So it's exactly the same, almost exactly the same. Let's say the same modulus efficiency with the coin tossing example. The probability mass function here is going to be this. Okay, so this dx given theta, which is the density, is really probability mass function. It's a density with respect to the counting measure. If you want to be careful, everything is a density, but like it's really a probability of observing X, like X heads out of n trials. So hopefully people know this, or you can look it up. That's the PMF. So what we do, for example, we can put a prior. We need to put a prior on theta, and theta is the range is in 0, 1, right? So I need a distribution that puts mass in 0, 1, and a good parametric family of distribution of 0, 1 is the beta distribution. Okay, so we put a beta prior, and this is the density of the beta prior. And if you ignore the normalizing constant, it's proportional to theta alpha minus 1 times 1 minus theta times to the power beta minus 1. And if you plot this, so this has a mean. So the expectation of theta, anyone remembers what the expectation of, so the prior expectation of theta, expectation of the beta distribution, what is it? Yeah, alpha over alpha plus beta. So one of the things that you can do, sometimes it's hard to come up with the entire shape of the prior, but you might choose this prior. As we'll see, this is a special like type of prior. It's conjugate to the binomial family. So it turns out that the posterior simplifies. So you pick, for example, the prior by conjugacy consideration, but then you can set the parameters by some knowledge about theta. So if I know, for example, my guess is, for example, that theta is like close to 1/2. I can choose alpha and beta such that alpha over alpha plus beta is 1/2. So I can set the mean of the prior. So these are called the hyperparameters of the prior. You can see we have to, like, we need to set this to something, alpha and beta. And you can choose that based on like the moments of this, for example. There's also a variance of theta. There are two parameters. So the variance also has a formula. If you have a guess of what the expectation of the variance should be, you can set them equal to that. Or like set these expressions alpha beta set equal to those and solve for alpha beta, and you would have like a fully specified prior. So these distributions, so this includes the uniform case, like uniform distribution is an example of this, right? Anyone sees why uniform distribution is a special case? What alpha and beta give me the uniform distribution? Just flat. Alpha equal beta equal 1, right? If I said alpha equal to beta equal to 1, the powers of these would be 0. So I get 1 everywhere. You have to normalize it, but once you normalize it, it would be 1 as well. And the shape and alpha and beta are less than 1. You'd see that this blows up. If alpha is less than 1, you get 1 over theta. As you approach theta, it blows up. So the shape would be like this. Blows up if you approach 0 and 1. That's like alpha and beta less than 1. And it's going to be like this. It's going to be 0 if alpha and beta are bigger than 1. Okay, so you can get these. And then if alpha and beta are equal, it's going to be symmetric, but it also equally, well, it could be like non-symmetric, could be like that. It doesn't have to be symmetric. You can see, like, I can shape the mean. So the mean could be very close to 1. Okay. You can get all sort of interesting shapes here. So go it out like this. Right. It's just going to integrate to 1. So it's a well-defined distribution for alpha beta bigger than 0. So yeah, that prior. Questions? So that's the prior. And the likelihood would be proportional to theta. I think this proportional, like as a function of theta. So I can say that this is proportional to theta x to 1 minus theta to the n minus x. I can ignore this constant, right? Because that doesn't depend on theta. So the likelihood is really of this form. And the prior you can see is of a similar form. So that's the idea of conjugacy. So the prior is the same form as the posterior. So once I multiply both, right? So if I multiply the likelihood by the prior, you can see that I'm just going to add up the exponents, right? So you get x plus alpha minus 1 here for theta, and the other one would be n minus x plus beta minus 1 here. Okay, so the form of the posterior, the functional form is the same, the parameters are different. Because the form is the same, the posterior would be another beta distribution. Okay, once I normalize it, so that the beauty of doing this calculation without worrying about constants is I don't need to care about the constant because I recognize the form as a beta distribution, and I know that there's some gammas there, like a ratio of gammas or a beta function basically that normalizes this. So as long as this is positive and this is positive, which is for us, and so we recognize the posterior is a beta distribution with these parameters, x plus alpha and n minus x plus beta. Okay, in this case we were lucky and we have a closed form, right? Closed solution, a closed form solution. So formally, what conjugacy means is, so it's a pair of likelihood and prior such that the posterior remains in the same family as the prior. Okay, so we have the binomial family is a conjugate to beta family. So this is prior, this is the likelihood, and so conjugate means that the posterior remains in the same family. Okay, posterior is beta again. And traditionally, this has been very common because it was hard to sample from general posterior. So people tried to come up with conjugate prior so that they know the form of the posterior so they could do the analysis. It's still helpful in more complicated models because it simplifies some of the inner calculations that you need to do. Oftentimes conjugacy would simplify things. So we have that, and then the base rule, let's say for quadratic loss, would be the posterior mean, because we recognize that this is a beta and we know what the mean of a beta distribution is. I just applied that idea to this. So it's going to be, the mean of this would be this plus the sum of the two parameters. So if you sum the two parameters, you can see x cancels out, get n plus alpha plus beta, and the numerator would be x plus alpha. So you can see it's a function of x, as you'd expect. And this is your rule, decision rule, right? Your base decision rule. There's a great deal of like intuition that we could build here, depending on how much time you want to spend on this. We can write this. This is an estimator. Okay, it's an estimate of theta, basically an estimate of the probability of the coin coming up heads. I can write it in this fashion as well, where lambda is this quantity which is between 0 and 1, and this has the advantage of making it clear that this posterior mean is really a combination, a linear combination of the maximum likelihood estimator and the prior mean. Okay, so our prior had a mean, and I'm trading off that with the maximum likelihood, which is completely determined by the data. Okay, so the data comes in, it pulls the mean of the posterior away from alpha over alpha plus beta, which is the prior mean, towards the x over n. You can see as n grows, this is going to go to 0. So 1 minus alpha, 1 minus lambda is going to go to 1. Okay, at the start, when the sample size is 0, right, lambda is 1, okay? So lambda is 1, this term is gone, so you just have prior mean. As you get more and more samples, alpha starts to move towards 0. So the weight of this gets smaller, the weight of this gets bigger, until you, like in the end, asymptotically, it's not going to be exactly maximum likelihood for any finite sample, but asymptotically converges to the maximum likelihood, or like gets close to the maximum likelihood. And you can see a lot of other things. So x over n here is, hopefully you know that this is now like the unbiased UMVU. So it's the uniform minimum variance unbiased estimator. This is unbiased. So how about this Bayes rule? Is it unbiased for theta?
No.
No, why?
I mean, you're always gonna have some alpha over alpha plus beta in your estimate.
Right. Okay. So the expectation of delta lambda x would be 1 minus lambda expectation of this part, right? The maximum likelihood estimate. Let me write it as theta hat MLE. So expectation of theta hat MLE. So unbiased. Okay. So I should be a little bit careful. Bias and unbiasedness, these are all for like frequentist perspective. We're now putting our frequentist perspective hat. So from a Bayesian perspective, there's no bias. Bias is like not meaningful. This is the posterior, this is it. If you're a frequentist, there is a true theta. Okay, there is a true parameter theta. Under that true parameter theta from the family, this is going to be that. We know that this is going to be theta. And because lambda is not going to be 0 ever for finite n, there's going to be always this extra term. Okay, so it's not going to be exactly theta. So this is going to be from a frequentist perspective. So from a frequentist perspective, delta lambda is a biased estimator. Intuitively, you can see it's like bias towards the prior biases thing. But that's not necessarily a bad idea. Okay, so it has some sort of a regularization effect. So you can also like see that it minimizes, like it reduces the variance, because like if this is very large, this is constant, the variance of this is like 0, right? So adding this like dampens the variance of the estimate. So it's very useful if your sample size is small. That's why, for example, Bayesian approaches are popular. When you have very few samples like these, like for example, clinical trials where you want to give drugs to people, there's toxicity involved. You don't want to like give the drug to like 1,000 people because you don't know like how toxic it is. You test it on like 2 people and then assess like small doses and then increase the sample size by 2 or something like that. So in the start, you have like this could be really like a toxicity of a drug. Coin tossing is like very benign, but this could be like I'm giving a drug to people and they either like it's a cancer drug, right? And people develop like symptoms or not. So it's like either toxic or not, 1 or 0. And you want to like estimate the probability of that at this given dose, let's say. There are multiple doses, let's say. But this is for a particular dose. And at the start, you give it to 2 people, for example. So you have a very small sample size. This is not going to be a very good estimate. It could be like 0 people end up being toxic, but doesn't mean if you have like 2 people, n is equal to 2, x is 0, your estimate of theta is 0. But you probably could guess that it's probably not 0. It's like something is small, but your sample size is not big enough. So there the prior comes in. If you have some prior information from other drugs, so this would like correct it a little bit. But eventually, as you get more and more samples, you want to downweight the prior. So this automatically balances out the prior and plus thing. So this has a lot of intuition, a lot of interesting ideas, and you can see they're more like generally biased. Bayesian approaches are biased, so that's why frequentists are a little bit, but traditionally has been a little bit bothered by it, because if your prior is not good, then you're biased in the wrong direction. So it sort of matters. But in the end, we'll see, for example, because the MLE is consistent and it's converging to 0, this is going to be consistent estimated as well. So asymptotically, everything is fine. Okay, this is no coincidence. It happens in general, I believe, in exponential families, but we're not going to go there as much. There's another point here is that this, you can see there's this alpha plus beta that's getting added to n. So sometimes people say this is the prior sample size. It is as if the prior brings this much information. Okay, it's not a sample size, but it acts like a sample size. So you can think of it as a way of like balancing out the information between the prior and cluster. Yeah, yes.
I just have a question. So the decomposition you're saying is this a feature of having a conjugate prior to an exponential family, or that's the beta?
That's a good point, and I'm not being very careful here. So I don't have a general result, but so take it with a grain of salt. But this, for example, we'll see another example in the normal family. But to make it precise, we have to like say something. Let's say put this in general, in parentheses, because the general would be a little bit tricky. Let's not dwell too much on it. It's not a precise statement, but I'm going to give you at least one more example. Right, you get like a statement with sample size 2, so at least 2 cases for which this happens. So this other example is the Gaussian case. Suppose you have a normal family, and the normal location family xi's are conditional on theta are from this normal family, and then with a Gaussian prior on theta, the conjugate family to Gaussian, like normal, is normal. So you put another normal prior on theta, and this has a mean and a variance. So these are hyperparameters. So the parameters of the prior are called hyperparameters. So it's not hard to see that. So you know that, for example, this location family is basically theta plus wi. So if xi's are from normal would mean theta and variance sigma squared, then I can write xi as theta plus wi, where wi is normal, which means 0 and variance sigma squared. The sigma squared here is also fixed, it's not a parameter. So if I think of it this way, so you could calculate posterior exactly using this formula. Write down the likelihood, write down the prior, and so it's a good exercise to do it here. So P of x given theta would be the product, I from 1 to n, P of xi given theta, and then pi of theta would be another Gaussian. You multiply out, so pi of theta given x is proportional to P of x given theta. Times pi of theta. As an exercise, I encourage you to do this. And it turns out that the form of this posterior is going to be e to the negative some quadratic in theta. So it's a Gaussian again. Here, what I'm like advocating, which is it's very special to this Gaussian family, is to write it like that. This is like conditional on theta, right? Xi given theta equal to theta is like that. Then you can just replace it here with just theta. That would be your general model, where theta is independent of wi. You can easily argue for yourself that if I have x given theta normal and then I have theta, it's like having xi being equal to theta drawn from the prior plus an independent Gaussian noise, which is 0. That specifies the full joint distribution. Because I have this relation, you might know that because I'm assuming that this is Gaussian and it's independent of these, the joint distribution of theta and so theta and W1 up to Wn would be Gaussian, independent Gaussians. And then theta and x1 up to xn is a function of this vector. So you can write what the function is, like a linear function. And so this would be jointly Gaussian. And then once you have a jointly Gaussian family, you can figure out the conditional distribution of any part given anything else. There's a nice formula in terms of the covariance matrix and stuff. Okay, so Wikipedia tells you that the posterior would be Gaussian in a jointly Gaussian family. The conditional distribution of any part given any other part is Gaussian. And their formulas, you just have to figure out the mean and the variance. And the covariance matrix of disjoint distribution, which you can calculate from the covariance matrix of this, which is diagonal, gives you all you need to know, okay, to calculate the mean of the posterior and the variance. So this is a very good exercise, both approach 1 and approach 2, via the properties of the multivariate Gaussian distribution and the conditioning in that to figure out both this is going to be the posterior is going to be Gaussian, and I can again write down the mean as a linear combination of x bar and mu. Mu is the prior mean, x bar is the NLE, it's the frequent estimator, the UMVU, etc. And you can see that this is going to be my Bayes rule on the quadratic loss. It's the posterior mean. And it can be written as a linear combination. It's called, in fact, it's a convex combination. So it's a combination with elements, like the coefficients are non-negative and they sum to 1. It's just a weighted combination with a special property. So it's a convex combination of the prior mean and the MLE. And this 1 over tau tilde n squared is going to be like that. So, so this is the variance. So inverse of it would be the precision. Okay, inverse of the variance is called the precision. So the precision is going to be added. So you get n times gamma here is, so gamma is the inverse of the variance of the model. That's the precision that the likelihood brings. And 1 over b squared, which I'm going to call tau or tau squared here, is the precision of the prior. So you can see the precision of the posterior is n times the precision of the prior, like the likelihood. So you have n samples, you get this much plus the precision of the prior. And again, as n increases, this is going to go to infinity. And this lambda, which is the ratio of the prior precision to posterior precision, this is going to go to 0. As you approach the MLE. The other thing to note is that this precision is really getting high. So your variance is shrinking. So what happens is originally you'd have like you had a mean here, and maybe you had a diffuse prior that has like a precision tau. As you get more and more samples, maybe x bar is like getting close to this point. This is like maybe theta star or mu star. The true mu, let's say, is here. X bar gets very close to this, and your posterior is going to be like this. So it's going to be like originally it's like gonna shift slightly, slowly, like maybe at first x bar is here, then so x bar moves. So x bar is here. It's gonna move it a little bit here, and then as you move closer to that, you move closer to this, and also precision goes up. Okay, so you move towards the true mean, and also like the precision grows. So your distribution becomes sharper, like concentrated sharper and sharper around x bar, which is also getting close to mu star. This is called posterior concentration. You can see the posterior concentrates in the sense that the variance goes down. And so it achieves both, like that's why Bayesians like their approach, is because it gives you also like a uncertain quantification, how uncertain you are. Originally, you were quite uncertain because maybe your prior was like this. You had 2 samples. It's like like moved a little bit and got narrow a little bit, but not too much, like narrower than the original prior, but not too much. But eventually, as you get more and more samples, this is gonna move and also like very sharply concentrate around. Maybe the other one is gonna be better to write it like this. It's very close to mu star. So as you move, like get more and more samples, you move and you also like become more certain. So posterior contraction or concentration. So this argument that I just made is from a frequentist perspective again. There is a real mu star that's generating data, assuming that then the posterior can show the posterior shrinks and approaches the truth. So this is called a frequentist analysis. Like what I just sketched is called frequentist analysis of a Bayesian procedure. Okay, a frequentist consistency of a Bayesian procedure if there is a true parameter. If you get more and more samples, eventually you're going to converge to it in the sense that the posterior is going to approach, the mean is going to approach there, and then the variance is going to shrink. Yes.
So does that mean when you have a lot of data, when n is large, that your choice of the prior isn't as important?
Yes, that's exactly what it means. Yes. If you have a lot of data, the choice of the prior is not as important as when you have very few data. So when you have very few data, the prior influences the estimate very much. Then you have a lot of data, you're putting a very little weight on it. So it matters, just one point. It matters if your prior is not putting mass where it needs to. So this is going to be very problematic. Let's say from a frequency perspective, if mu star is here, your prior is like this, and it's just zero mass here. You're never going to capture mu star. Okay, so you're gonna like, if you write down your posterior, it's a very good exercise. It's gonna, as you get more and more samples, it's gonna like approach this, but it can't like move beyond the support of the prior. So it's very good to have like a diffuse prior, like put mass, a little bit of mass like everywhere. And that makes it very hard to design priors for like big spaces. Like if you have a function space, how can I spread mass all over the place? It's not easy. Like a compact space, like compact interval, it's easy to put mass everywhere. So the beta would do that. Maybe not at this point, but it's just if you have a beta distribution like this, the only things that you miss are the zeros and ones, like the perfect coin. But everywhere else there's mass, so you're going to recover anything. But if your space is hard, like high dimensional, infinite dimensional, it's going to be much different. Yes, good question. Yeah.
Is there a reason it looks like it's doing a harmonic mean thing? Or it's 1 over, like 1 over.
Yeah, it's interesting. I not sure, to be honest. Yeah. Yeah, the Gaussian case is very special, so there might be some meaning to it. I don't know. This makes a lot of sense. So intuitively it makes a lot of sense. The precision just adds up. Precision of prior plus the precision of every bit of data that you get. So each one, like if IIDs it brings this much precision, so your precision just linearly adds up. But why it's like in terms of the variance, it looks like harmonic. It's not exactly harmonic mean. There's factor of 2 missing. But yeah, I don't have a good answer there. Okay. Questions? So this last point that I mentioned that came up is important. It's tricky, and so the prior eventually doesn't matter as long as there is a little bit of mass there. But if you have a very small amount of mass here, it's going to take you a longer time to approach. Whereas, so intuitively, you would like, if you don't have any information, to uniformly spread the mass, but that would be tricky. Actually brings us to yeah, so this talks about conjugacy. Let's skip that. We can read about this. You saw normal beta binomial. The extension is Dirichlet multinomial. So beta is like a special case of Dirichlet in a sense, beta 1 minus beta, basically. That would be like a two-dimensional Dirichlet distribution. Dirichlet is a distribution on the space of probability measures or probability vectors. And binomial extension with multinomial. So this is very common, Dirichlet multinomial conjugates. And there's a way to write down the formula for a conjugate prior in a general exponential family. It doesn't look as nice, and it's not always going to give you like a closed form solution for a family, which so this really might not be like easy to calculate, and it might not be a recognizable family, but in principle, you can write down a conjugate prior, because if you multiply these two, you'd see that this gets added to this, and this B gets added to A, or if you have n copies, you get n here, and then n and B add up. So by looking at this form, you can come up with this. You can see that the product still remains within this family with A and B of beta. But let's just leave it at that. So there is some conjugate prior there, whether you want to use it or not. It's a different story. So this brings us to this idea of improper prior. So the fact that you want to like spread the mass everywhere. If you have like the real line, for example, uniform distribution on the real line will be basically the Lebesgue measure. But the Lebesgue measure is not a probability measure, right? So if I want to have probability measure, I have to taper things down at the infinity, right? So Gaussian is a valid probability distribution, but I can't just have uniform mass everywhere. I can have, but I'm going to be outside the probability land. This is going to be like a Lebesgue measure. So the measure of the entire line would be infinite. Well, what if I want to use this? So you can use this, and this would be like what they call improper priors. Okay, so if you have p theta given x, and then pi of theta, and then you have p of, say the posterior is going to be proportional to that. So you can just pretend that this density is 1. And then if the posterior integrates, so sometimes the likelihood is sufficiently concentrated that I can integrate this to 1. So it turns out that the integral of this guy, d theta, is finite. Then I can normalize it to get the probability distributions. I can pretend that this density of 1 is really a prior, because it gives you a valid posterior. So these are called improper priors. And they're interesting because, for example, the MLE in this family is not a Bayes estimator for any proper prior, that's a probability distribution. But you can see that, for example, if I have like a 1 there, the MLE would be the Bayes rule for this improper prior, if you do the analysis. So the decision rules that you get out of these improper priors sometimes called generalized Bayes rules. And so you can either assume, let's say if you want to recover the NLE as the Bayes estimator, it's going to be the limits of Bayes estimators for some sequence of priors, or for example, beta binomial case, you can see that. Or you put these improper priors. The other reason why you would want to do it is because of the uniformity. So you want to like have a uniform distribution. Things are a little bit murky here. So like formally, they're not like the machinery of the probability is not working properly, but you can still work with this posterior as if it's posterior. Whether you're comfortable with that or not, it's up to you. But just know that these exist. Sometimes you can come up with a prior that doesn't integrate to find something finite, or if it's integrates something finite, you can always normalize it to get a probability distribution. But if it doesn't, it could still be that the posterior integrates, pretending that that formula holds, and then you would get some sort of posterior that you can work with. I assume true Bayesians wouldn't use these, but they're just there. There are other things, considerations that we're not going to go into, things like Jeffrey's prior, which I have trouble writing his name, Jeffrey's prior, or like reference priors. these are ideas of trying to come up with priors without like objective priors that don't require any like priors are supposed to encode your subjective information. So the information that you have, if you don't have them, how to come up with priors, people try to come up with criteria to have some sort of an objective way of coming up with priors. Jeffries and stuff. I think Jeffries is like this. So you can read about them. I usually don't talk about them. But this is like, again, more of a frequentist way of thinking. So you want to come up with a prior as a device, which is like usually you want to spread the mass, like you want to make the prior the most uninformative. So these are called uninformative priors. The least amount of information, like the maximum entropy principle that we discussed. So let's just leave it at that. So any questions about the mechanics and machinery of Bayesian approach? Yes.
I guess not to belabor the picture, but interesting about like delta could be like a limit point in the sort of space of Bayes estimators, but it doesn't live inside the space of Bayes estimators.
Yeah. So properly speaking, yeah, this is not a Bayes estimator. Yes. Yeah. So it's like at the boundary of yeah.
Thanks for raising the question, like what is the space of Bayes estimators for? Like
I'm gonna hopefully talk about this shortly. Not the space of Bayes, but I'm going to talk about the risk. So there's a picture that we have later that tells you like about the geometry of these things, which might help. Okay, that's a good point. But Bayes rules are good. The totality of Bayes rule. So the collection of Bayes rules as you vary the priors. That collection is a desirable collection. The good estimators are within that, or like close to that. You can approach good estimators with that. We'll see, like hopefully like by the end of this. That's hoping to end like by the end of this lecture, but it seems like we're not going to get there. But once we talk a little bit about the connection between the minimax and Bayes, you'll see that, for example, the minimax would also be a Bayes rule for a particular prior. Okay, we'll get to that. This is about the uniqueness of the Bayes estimator for convex losses. I'll let you read it for yourself. It's not that tricky. Let's go talk about the minimax idea. And so we talked about the Bayesian approach, and we're going to come back to the Bayesian approach. But let's also see what the minimax criteria would be. That's like a frequentist approach to try to deal with the idea that the risks are functions and try to summarize or reduce the risk to a number so that we can compare the estimators. So the Bayes, like the minimax risk is formally something like that, right? So supremum over, so we're back in the frequentist land. So the risk is like a function of theta. That's our usual risk expectation of the loss, theta and delta. And then I take the maximum over theta, that's the maximum risk. I'm using this notation, which is not necessarily a good notation, but again, it just depends on delta, really. There's no other dependence. Now it's a number I can minimize over delta. Okay, so I can ask what is the minimum of this? And the minimizer, delta star, would be the minimax rule. So if we ignore the sup and inf, like min and max, you'd see the delta star would be, probably delta star is up there is better. Delta star would be min over all decision rules, max over theta of r, theta, and delta. That's why it's called the minimax. If we take the maximum for a particular delta, we take the maximum, that would be my maximum risk for that particular decision, and then I'm going to minimize over delta. Okay, that's the criteria. So we want to talk a little bit about how to actually find these things and surprisingly, there's a good connection. There's a nice connection to Bayes rules. So Minimax is clear criteria. So I'm going to do it a little bit differently than I have it on the slides. I just want to maybe show you why there's a connection. So let's think about the case where we have a finite parameter space. Okay, this is the easiest case, and we'll also see that the geometry of the space is much nicer if you have this, or like it's easy to visualize this. The finite case. So then the risk of an estimator would be, you can represent it by a vector. So these are functions of theta, but then there's only k values, so you can represent it like this. Later, I'm going to write it as rho of delta. So this is, you can think of it as the risk vector. It's a k-dimensional vector. So if you have two parameters, for example, it's just going to be a two-dimensional vector. So this is the easiest to think about, maybe k equal to 2 throughout. And what I can do is now say that the maximum risk basically of delta, which is just the maximum over I of these theta I delta, is just the infinity norm, if you want, of this rho delta. So if you remember what the infinity norm is, right? The infinity norm of a vector, what is the infinity norm? Yeah, so if you have a vector y, the infinity norm is the maximum of the absolute value of the elements. I'm assuming that the risk is non-negative. The risk is non-negative. And so the absolute value doesn't matter. So I can put absolute values here. And you can see this is just really the L infinity norm of this. So the minimax problem would be min over delta in D. This is the set of decision rules. And then instead of the max, I'm just going to have this infinity norm. So this is the minimax problem. And okay, so why this is interesting, because there is a duality relation. So this is dual to some other norm. Anyone remembers or like knows what duality of norms mean? Like what is the one norm? So what does it mean to have the dual of this being the one norm? Right, the maximum of, let's say, y and some other z here. Write it as lambda, for example. Lambda is another vector. If the L1 norm, if I take the maximum of this over the L1 ball, this is several lambdas such that the L1 norm is less than 1. This is the L1 ball. So this is saying that the maximum of the linear function over the L1 ball is the infinity norm. Okay. This is the duality relation. Another way of writing it is that y lambda, this is another vector in RK. This or either this or absolute value. I can put absolute values here, it doesn't matter. This is bounded by y infinity lambda 1, and equality holds for some, for any y, equality holds for some lambda. Why this is like that is because if you basically divide by the norm of lambda equal to the norm of lambda, the norm of the L1 norm of lambda, then you'd see that the maximum of this, so over all the lambdas for which the norm is at most 1 is going to be this, and if the inequality holds. So this inequality is, what is this inequality? Yeah, generalization, which is called the Holder's inequality. So Cauchy-Schwarz would say this is less than or equal to y2 times lambda 2. Okay, or if you want to write it in the fashion that I wrote, Y2 is max over the L2 ball of Y lambda. So this shows that L2 is self-dual. So dual of L2 is L2, dual of L infinity is L1, and duality like a symmetric thing. Like dual, like not symmetric, but like dual of L1 is L infinity. The role is symmetric, especially in these inequalities you can see. So the general idea is like there's a P here and there's a Q here, right, in the holder, and LP and LQ are dual to each other. This is the extreme case where one is infinity, the other is one. Okay, we're out of time, but just let me point out maybe 1 minute. So why this is important, because I can write this as min over delta in D, max over lambda L1, lambda transpose rho delta. And if you think about this, this is really the Bayes risk of delta with respect to the prior lambda. Okay, that's, I'll leave it to you, like, because we're out of time. Think about this, post these slides over the weekend. Think about that this turns out to be the Bayes risk of delta with respect to prior lambda. There's a little bit of idea here that lambda need not, because this is positive, I can replace it with a delta, with a lambda which has positive coordinates. So I just need to consider lambdas that are in R plus, and also need to only consider the things that are equal to 1. But if you just argue this for yourself, the maximum over all the L1 ball is achieved over really the probability vectors. Once you have it, if you restrict to this class, which is equivalent to this, in this case, because it has positive coordinates, then this would be Bayes risk with respect to lambda. So there's this nice connection between the Minimax problem and the Bayes problem. So I'll post these, think about it. Next time we'll come back and continue.